need to evaluate this surface integral where S is a part of the sphere x square plus y square plus z square equal to 1. That is the unit sphere. Above the xy plane. This is very important. It is given to us that this sphere is above the xy plane. So when the sphere is above the xy plane, we always take z coordinates to be positive. Okay, so this f vector is given to us and the surface is of the part of the unit sphere which is above xy plane, and we need to evaluate the surface integral. So again we are going to take the help of the Gauss's divergence theorem over here. So let's consider V to be the region enclosed by surface S. Then by Gauss's divergence theorem, let me write the result first. It is the surface integral of dot product of f vector with n vector ds is equal to the volume integral of divergence of f vector. And the same can also be written as, because we know that n vector ds, this is equal to dA vector, where dA vector, this is the vector area and ds is the magnitude of the area, right? If I multiply n vector is the unit vector along the normal to the surface, right? And if I multiply this n vector with ds, that is the magnitude of the area, I get this to be as the vector area, right? So we can also take this to be equal to the surface integral of f vector dot product with simply dA vector. Either you can use in this way or you can use in this way. It's up to you. Because it is given to us that f vector is having the dot product with dA vector, so I am going to use in this way, right? So to evaluate the surface integral of f vector dot product with dA vector, so this is equal to the volume integral of divergence of f vector using Gauss's divergence theorem, right? Okay. So the volume integral of divergence of f vector is del dot f vector dv. Writing del as curly over curly x I vector plus curly over curly y j vector plus curly over curly z k vector, and its dot product with f vector, which is given to us this one, y square z square I vector plus z square x square j vector plus z square y square k vector dv, right? When we take the dot product, we get curly over curly x of y square z square plus curly over curly y of z square x square plus curly over curly z of z square y square dv. So derivating y square z square with respect to x, it gives 0. Derivating z square x square with respect to y gives 0. Derivating z square y square with respect to z gives 2zy square. So this is equal to the volume integral of 2zy square dv. Taking this to outside, and then we are going to write this as the triple integral of zy square, and writing dv as dx dy dz. Because I am having z at the first place, so I am writing this as dz dy. It's up to you in whatever way you want to do. And the surface given to us is the part of the unit sphere x square plus y square plus z square is equal to 1. Let's first write the limits for the innermost integral, that is the integral with respect to x. So for that we are going to write the limits for x. So from here we get the limits of x to be, it is 1 minus y square minus z square under the root with plus minus sign. So the lower limit of x is negative of square root of 1 minus y square minus z square. and the upper limit is square root of 1 minus y square minus z square. So we have already used the limits for x, and now we are going to write the limits for z. So we are interested in now zy plane. So for zy plane, this x is 0. So from here we get the limits of z to be as 1 minus y square under the root with plus minus sign. So the limits of z is plus minus square root of 1 minus y square. So writing the limits of z as minus square root of 1 minus y square, the lower limit, and the upper limit is 1 minus y square under the root. And at last, writing the limits for now y. So already we have written the limits for these two innermost integrals. So we are now only interested in y-axis, and for y-axis we take x and z to be 0, and from here we get the limits of y to be as plus minus 1. So the lower limit is negative 1 and the upper limit is 1. It is okay, fine? Alright. Because it is given to us that this unit sphere is above xy plane. So for above xy plane, we always take the limits of z to be positive. We take the coordinates of z to be positive. So the limits of z will start from 0 to square root of 1 minus y square. So it is from 0 to square root of 1 minus y square. Is it okay, fine? Yes? Okay. So let's solve this triple integral now. Let's solve this innermost integral first. Because this integral is with respect to x, so for that zy square is constant, I am taking this outside and integrating 1 with respect to x. So that gives x. And the limits minus square root of 1 minus y square minus z square and square root of 1 minus y square minus z square. On putting the upper limit and the lower limit, we get this to be as twice of square root of 1 minus y square minus z square. So this is twice square root of 1 minus y square minus z square dz dy. And I'm going to take this 2 outside and we get 4. Let's use the substitution method to solve this integral with respect to z. For that, put 1 minus y square minus z square equal to t. And then we get minus 2z dz equal to dt. Y square is constant for this integral, so writing this y square outside of this integral, and because I need to have minus 2z dz and I'm already having z over here, so I need to multiply and divide by minus 2. So here I get minus 2, right? Fine? Okay. So writing this as square root of t, and this becomes dt, and this is dy, and the limits become, for z to be 0, we get the limits for t as 1 minus y square. And for z equal to square root of 1 minus y square, we get the limits of t to be as 0. So this is equal to minus 2 minus 1 to 1 integral y square. Okay, integrating square root t with respect to t, we get t the power 3 by 2 divided by 3 and here 2. This is dy, and the limits are 1 minus y square and 0. So putting the upper limit, we get 0, minus putting the lower limit, we get 2 by 3 into 1 minus y square the power 3 by 2. So we get minus 2 integral from minus 1 to 1. And here on putting the upper limit, we get 0, minus when I put the lower limit, I get 2 divided by 3, 1 minus y square the power 3 by 2 dy. And y square is also multiplied with this, right? So this becomes minus 2 integration minus 1 to 1 y square into minus 2 by 3, 1 minus y squared the power 3 by 2 dy. Taking this negative 2 by 3 outside, we get 4 divided by 3, integral minus 1 to 1, y square into 1 minus y squared the power 3 by 2 dy. And because this is your even function, and for the even function, if the limits are same with opposite sign, then this integral becomes twice the integral of f of x dx, and the limits are from 0 to 1. So using this result over here, so this becomes 4 divided by 3, twice this integral, limits from 0 to 1, y square into 1 minus y square the power 3 by 2 dy. Fine? Yes. And this becomes 8 divided by 3. Again by substitution method, let's put this y to be sine of theta. And then we get dy to be as cos of theta d theta. Right? So limits of theta will be, if y is equal to 0, we get sine of theta to be equal to 0. And when the sine theta is 0, when theta is 0, 2. For y equal to 1, we get sine of theta to be equal to 1. And when sine of theta is equal to 1, when theta is pi by 2. So this is equal to 8 divided by 3. Limits from 0 to pi by 2. And y square becomes sine square theta into 1 minus sine square theta is cos square theta, the power 3 by 2. And then dy, this is cos theta d theta. Right? So this is equal to 8 divided by 3, integration from 0 to pi by 2, and this is sine square theta. This gives cos cube theta, and this is also cos theta, so we get cos the power 4 theta d theta. Now I am going to use the reduction formula. For that, the limits should be from 0 to pi by 2. Then only you can use a reduction formula. So that is equal to 8 divided by 3. Alright. Here I am having the power of sine to be even, 2, right? So we have to subtract the odd numbers from the power for the numerator. So this is 2 minus 1, that gives 1, right? Okay, till we get 1. Now the power of cos is 4. Again we have to subtract the odd numbers from the power for the numerator. Okay, so 4 minus 1, 3. 4 minus 3, 1. That's it. Stop here. And because the power is even, so pi by 2 is also multiplied with this. Please remember this. Then for the denominator, we add the powers first. So 4 plus 2 is 6. And then from this addition of the powers, we need to subtract the even numbers, right? So subtracting even numbers from 6 now. So 6 minus 2 is 4. 6 minus 4 is 2. That's it, right? These are all multiplied with each other. So cancelling this, 3 is cancelled by this 2. Then we get 2 4s are 8. So this is pi divided by, this is 3 to the 6, 6 2s are 12. So pi by 12 is the required answer to this problem. Thank you.